All right, we're going to keep moving on in chapter 16. What's going to be nice about section 16.2 here is that it's going to be very, very similar to what we were doing in 16.1. We're going to be looking at these double integrals over regions. The big difference here is that we're going to define our regions with functions versus just having those regions being rectangular. So that's where our first learning objective comes in there. We're going to look at regions that are defined with equations. We're going to then choose an order of integration because sometimes it's going to be easier for us to integrate with respect to x first versus y. Sometimes that's going to have to do with the surface that we're integrating over. Sometimes that's going to have to do with actually the region that we have and how easy it is going to be to set up the integral over that region. Um, and I have the area by double integral. I think we're going to look at that one in class. So our definition, I'm not going to go into a huge, really complicated definition because it's very, very similar to what we did in 16.1. But I've got an example of several different kinds of regions that we can have um, that we're going to integrate over. So again, what we're doing is we're looking at a space or a region in our XY plane. And I apologize, I grabbed these from a book that called their region D for domain versus our book calls it R. It doesn't really matter if you call it R or D. It's just talking about the how you're going to restrict your domain of your function, sort of what X and Y values we're actually going to look at. So the idea is, that we can have, say, sort of functions like we're used to. So y equals, something in terms of x, and that's our bottom function. And then we've got a top function, y equals some other function of x. And then we're going to look at it from x being a to b. And, we can have it, all different kinds of situations here. Maybe we've got one curve. Um, that maybe we could write as a function of y instead of just as a function of x. And then we've got maybe a vertical line on the end. So we still can sometimes have these be defined by vertical lines or horizontal lines, like down here in the case of, we can also have equations where it's x equaling something to do with y. So we'll see some of those as well. We could also say, look at a region that is bounded by two functions, like we've got, over here in this third picture. And we might have to actually maybe find points of intersection. So that might be a thing that we have to do with these. But really, basically, the idea here is we're going to have this region, and it's going to be some function f of x, y. Then we're looking at, again, that change in our area. So we could basically have, from a to b on the x-axis, and then from our lower function to our upper function. Oops, let me get my notation right there, upper function, and then f of x, y, and then this would be dy dx. If we were doing it in this order, we take our integral with respect to y first. Our answer would actually end up being in terms of x, and then we would take our integral with respect to x. And when we're looking at the limit of integration, whether they're functions or they're numbers, we always go left to right, so moving in that positive direction on the x-axis. We do the same thing on the y-axis. We go from that lower function to our upper function. We're always moving in that positive direction. So again, down here, if we're on the sides of our functions, sort of the vertical sides of our functions bounded by equations, we still are going to move left to right. So in that positive x direction. And same with the y's, we're going to move from that lower y value to our upper y value. And so down here, our region would be, get this written out, the integral from c to d, and then we'd have our h of y, our lower or our left function, and h sub 2 of y. And then we have whatever our surface is, and this would be a dx dy. So really, let's take a look at some examples of these, because that's really what we need to do, is just look at these in practice. I'm sorry, we're getting some ambient noise in the background. One of my cats is messing around in my blinds, so she's making a little bit of noise over there. All right, so we've got an integral, and it's going from 0 to 1. And notice our outside limit of integration is dx, so these are x values here, and our inside limit of integration is dy, and so these are our y values. So one of the things we're going to want to do with these uh, double integrals, especially when we've got these regions that are not rectangulars, we're often going to want to graph them. So it's going to be kind of interesting because some of the time you're going to be, basically doing some, sort of like linear algebra, not linear algebra kinds of things, like college algebra types of things, graphing lines, graphing quadratics, graphing power functions, doing those kinds of things. So when I was setting this up, I know that on the x-axis I'm only looking from 0 to 1. That's why I only did 0 to 1 there. I kind of know where I'm going, which is helping me do my y-axis. But what we want to draw in here is, so here are our limits of integration on x. So there's a vertical line there at 0 and a vertical line there at 1. And then we've got the equations, our y equations. We've got y is equal to x and y is equal to x to the fourth. So y is equal to x, that's pretty easy to draw. That's a line, goes through the origin, and looks like that. So there is y is equal to x. Let's grab a different color here. Y is equal to x to the fourth. Don't need to write it again. It's right here. So that also goes through 0, 0. At x squared, that's going to be pretty low. Yeah, that's going to be 1/16, or x squared, 1/2. And then at 1, it's going to go also through 1. And it's going to look like that. It's going to kind of look like a parabola, but it's a little bit shallower than a parabola. And so our region, oh, brother, it erased there on me. Our region is this region right here. So again, if you look at that limits of integration, we're going from our lower function to our upper function, and then again from 0 to 1 on the x-axis. All right, so just like with our other integrals, I'm going to do this inside integral first. So it's okay that our limits of integration are variables. We still want to take our integral with respect to y. So again, any x values, we're going to treat those like constants. So when we just have an x, that's like just having a 5, so it's going to get a y. And then our 2y, that is going to turn into a y squared. And we're still going to use the fundamental theorem of calculus. It's just our limits of integration are equations and not numbers. But what we do doesn't change. We plug in those x values in for y. So we're going to have x times x and then x squared minus x times x to the fourth plus x to the fourth being squared. So just like we would do if our limits of integration were 0 to 5. We plug 5 in for y, we plug 0 in for y. In this case, our numbers, which we'll put in quotes here, they're variables instead. So we are going to get, what, x squared plus another x squared minus x to the fifth minus x to the eighth. We do have some like terms here. We get 2x squared minus x to the fifth minus x to the eighth. So again, now we can replace this inside integral with this equation that we got from our inside integral and find the integral from 0 to 1 of 2x squared minus x to the fifth minus x to the eighth dx. And again, what we have now is an integral that we know how to take. This is a normal integral like we do all the time in 252. So we get 2/3 x to the third, 1/6 x to the sixth, minus 1/9 x to the ninth, and this is from 0 to 1. And again, we're at the fundamental theorem of calculus part of it. So what do we get? 2/3 minus 1/6 minus 1/9 minus 0. And doing our calculations, we're going to get 7/18. So this is pretty straightforward. This is set up for us. And sometimes they'll be set up for us. Sometimes we will have to set these up ourselves. So let's take a look at another one here. Or sometimes we have it set up and it's not set up the best way. So that's why it's good to practice on all of these, drawing this region, because sometimes we need to change our limits of integration. So on this one, if we had it just like it was right here and we wanted to do that inside integral, right, if we wanted to find the integral of the cube root of y from cube root of y to 2 of e to the x to the fourth dx, I don't know how to do this with the methods that we have right now. What I need is I need something like an x cubed out in front of my e to the x to the fourth to do substitution. Like I said, I don't know how to do this integral set up this way. So what I'm going to do is I'm going to swap my limits of integration. So let's swap these. Whoa, I can't write. So let's swap these. Now to do that, we can't just straight swap our limits of integration. We need to figure out what our limits of integration are, because this is x equals 2 and x equals the cube root of y. And this is y is equal to 8 and y is equal to 0. So what we need to do is look at this region and see how we would set this up a different way. So let's graph it. Okay, so I do look at that outside integral first because that tells me at least how far I'm going to have to go on my y-axis here. 5, 6, 7, 8. So there's 8. That's fun to get a call during doing a video. All right, so these limits of integration, you can draw those in as horizontal lines. They kind of give us like the lower and the upper kind of bounds of things, so that's moderately helpful there. And then graphing x equals 2, let's grab a different color here. So maybe there's 2 and there's 1, so I'm making my scale a little bit different. So there's x equals 2, that's a vertical line. X equals the cube root of y. Well, we could graph it that way, or we could take cube root of y is equal to x, cube both sides, and get y is equal to x cubed. That we can graph. Let's see, that goes through the point 1, 1, and it also goes through the point 2, 8. So that's going to be this. So again, these limits of integration right here are telling us we're going from this left-hand function over to our right-hand function. So that also tells us that our region is this inside region right here and not this part right here. That's how we know it's the inside one, because those limits of integration are kind of telling us how we're moving. So let's swap these. So this line right here is y is equal to x cubed, or we could even, both of those graphs are the same. And so now if I want to flip-flop these limits of integration, let's not write them in yet, just yet. So I want to go dy and then dx. So I'm going dy first. So the y values, they're starting down here at 0 and going until we hit that y equals x cubed function. So they're starting at the line y equals 0 and stopping at x cubed. And then our x values are going from 0 to 2. So notice our limits of integration look pretty different than they did over here. That's why it's really helpful to draw that region and think about, okay, now if I'm moving in these different directions, how is that going to change those limits of integration? So now we can take our inside integral, the integral from 0 to x cubed of e to the x to the fourth dy. And why this is easier is this I know how to take the integral of. Because I'm taking the integral with respect to y, that e to the x to the fourth, that's a constant term because our only variable there is x. So our integral is that e to the x to the fourth times y. And then we've got, our fundamental theorem of calculus. So we've got to do our 0 to x cubed. And again, this is just a matter of plugging those values in for y. So this is minus e to the x to the fourth times 0. So we just get x cubed times e to the x to the fourth. Now if we put this back into our inside integral, we get the integral from 0 to 2 of x cubed e to the x to the fourth dx, and now we can do substitution. We can do u is equal to x to the fourth, so du is equal to 4x cubed dx. So we need to move that 4 over with our du, and we get 1/4 du is equal to x cubed dx. So our x cubed and dx we can replace with a 1/4 and a du. So we get the integral from 0 to 2, 1/4. And again, I do a little bit of bad math. I don't change my limits of integration. You totally can. So we get 1/4 e to the u du, which is going to be 1/4 e to the u, again, from x equaling 0 to x equaling 2, or 1/4 e to the x to the fourth from 0 to 2. So again, now we just have to plug those numbers in. 2 to the 4th power, that is 16. So we get e to the 16 minus 1/4 e to the 0. Anything to the 0 power is 1. So we get 1/4 e to the 16 minus 1/4. Or sometimes you see this, people will factor out that 1/4. I don't really care either way. It's kind of up to you. But there is our volume under that surface. Okay, let's take a look at another one here. All right, so this time they're not giving us the limits of integration, so we're going to kind of have to decide what we think is the best way to set this up. So set up and evaluate the following integral. So here's our integral. Our function is just y, which is kind of interesting. But we want the region that's bounded by y equals x minus 2. So let's see, let's draw that in. We know that, that's a line. Okay, so there's that line. So we're looking for the area, or the region created by these two graphs. So there's our first one. And then our second one is x is equal to y squared. We can leave it like that, or you could take the square root of both sides. We have to do plus or minus. And we get that y is equal to plus or minus the square root of x. So the top part of that graph looks like this. That's the positive square root part. The bottom part of our graph looks like that. So there's our region. So I'm going to color that in just for a second, but then I'm going to erase it. So now the question is, how do we set up our limits of integration to have this make sense? Because both of these graphs, we could write them in terms of x or y. So this one is y equals x minus 2. It's also y plus 2 is equal to x. We could write that, the equation of that line, either way. If you graph both of those in Desmos, they're the same line. Same with this guy here. This would be x equals y squared, or it is y is equal to plus or minus the square root of x. Again, if you graph y equals x squared in Desmos, you do get that sideways parabola. To graph the other one, you'd have to graph it in two pieces to get the top and the bottom. So now the question is do we integrate with respect to x first or y first? Now, if we integrate with respect to y first, which is kind of, what some people's default is. Remember, when we integrate, let's get a different color here. When we integrate with respect to y, we go from the bottom to the top. So what's hard about this is right here at 1, before 1, the bottom function is that negative square root function, and the top is that positive square root function. After 1, after x equaling 1, the bottom function is that linear function, and the top function is our square root function. So we would actually have to do this with two integrals if we set it up with respect to y as our inside integral. So I don't know about you guys, I don't want to do that. So it's going to be easier for us if we set it up with respect to x first and go from the left to the right, because that purple graph, so maybe we'll write this down, that when we integrate with respect to x, we go from left to right. And this purple function right here, maybe we'll highlight it instead of drawing it that way. It is always on the left. And our green function is always on the right. So we're always moving from that purple graph to the green graph. So when we're setting up our limits of integration with respect to x, we want on the left is x is equal to y squared, and then x is equal to y plus 2. So I'm just writing those there with the x's just for right this moment. I will take those x's off of there, but we want them as x equals, because when we do our limits of integration for y, when we look at, sort of the lowest y value we get, the lowest y value is -1 and the highest y value is 2, we are also doing y is equaling to -1 and y is equaling 2. So we're doing that for both of those. Now, of course, we don't normally write it like that. Normally we write it like this, so that x equals and that y equals, those are generally, as we would say, implied. So now our inside integral, we're going to take that, so it's from y squared to y plus 2 of y dx. So y in this case is a constant, and our integral is x times y from y squared to y plus 2. And then again, it's a matter of plugging in those equations in for x. So we're going to get y plus 2 times y minus y squared times y. So let's see, what's that going to end up being? We are going to get y squared plus 2y minus y cubed. And again, now this equation is going to go in for that inside integral, because that's what we got from evaluating the inside integral. So now we're going to do the integral from -1 to 2 of y squared plus 2y minus y cubed dy. So we get 1/3 y cubed plus y squared minus 1/4 y to the 4th from -1 to 2. I'm assuming you guys can plug those numbers in. I'm sure you can. And you get 9/4, or as a decimal, 2.25. We will do a lot more examples in class. We'll look at swapping those limits of integration and doing all sorts of things.